Unaligned base model generate 100 or even 1,000 different answers to the exact same question, and they just check to see if any single one of those 1,000 attempts contain the correct logic.
And what happened?
When you do that, the raw base model actually overtakes the RLVR model.
Wait, what? So the base model actually knew the correct logical path all along.
That is the you et al. Argument. They argue that RLVR does not inject net new reasoning logic into the neural network. It merely acts as a sharp probabilistic filter. The correct logic was already hidden deep inside the chaotic noise of the base model's pre-training data. RLVR just alters the sampling probabilities so the model successfully outputs that latent reasoning on the very first try. It amplifies the good stuff and suppresses the noise, but it doesn't create cognition.
But the other side fiercely disagrees.
Yes, studies like you et al. Argue the exact opposite. They claim that with sufficient RL training over many steps, models undergo phase transitions.
Phase transition.
They discover genuinely new solution paths, novel exploratory strategies, and abstract generalizations that were demonstrably absent from their pre-training data. They firmly believe the reinforcement learning loop is creating net new cognitive capabilities.
It is incredible. The greatest minds in computer science have built a machine that can solve advanced calculus, and they do not fundamentally agree on how it is doing it. Are we creating logic, or are we just excavating it from the statistical noise of the internet?
It's a fascinating question.
Which perfectly drops us into the philosophical deep end. We have trained the model, we have aligned it, we have optimized its reasoning. Now you, the listener, are using it. You paste a dense 50-page PDF report into the chat box, and you ask the AI to analyze it. It gives you a brilliant, insightful summary. I want to return to our opening premise. Isn't the model learning from that PDF right there in the moment?
No. It is the most counterintuitive reality of the technology. At inference, when you are actively prompting a deployed model, the billions of weights that make up its knowledge are frozen, immutable. The model cannot learn.
But I've seen it. If I tell it a new rule, like respond to all my questions like a pirate, it remembers that rule for the rest of the conversation. How is it doing that if the weights aren't updating?
You are experiencing in-context learning, or ICL, and it is mechanistically, mathematically, completely distinct from actual training. When you type a prompt, that text lives entirely in the temporary activations of the forward pass.
Okay, let's unpack this forward pass. Because for years, this felt like dark magic. But the Google paper from July 2025, Darren et al., finally cracked the exact math on this, didn't they?
They did, and it is a masterpiece of mechanistic interpretability. For years, researchers wondered why in-context learning feels so much like gradient descent training, even though no permanent weights are updating. The Google researchers mathematically proved a duality.
A duality.
They showed that feeding context tokens into an attention layer, which then passes into a multi-layer perceptron, the MLP, the dense feed-forward layers where the model's actual knowledge is stored, is mathematically equivalent to applying a low-rank weight update to that MLP layer.
Wait, I thought you just said the weights aren't updating. Now you're saying the math says they are.
It is mathematically equivalent to an update, but it is entirely implicit. It is transient. The calculations happening in the forward pass simulate the mathematical effect of a weight update, altering how the downstream layers process information for that specific query. But it exists only within the RAM of that specific calculation.
So the moment you hit clear chat and the context window empties,
that implicit mathematical patch vanishes completely into thin air. The actual parameters resting on the server's hard drive never changed by a single decimal point.
This is where I want to use my favorite analogy. It is like putting on a pair of heavily tinted red glasses. You put them on, and suddenly your entire processing of the visual world changes. White walls look pink, blue skies look purple. The context, the glasses, has fundamentally altered your perception.
Right.
But your physical eyes haven't changed. Your optic nerve hasn't rewired itself. And the moment you take the glasses off, the moment the context window clears, the effect is gone instantly, and you are back to your frozen baseline.
That is a highly accurate representation of the transient nature of ICL. And it's vital we dispel some common myths around this for users. What about ChatGPT's memory feature?
You mean the feature where it remembers your dog's name across different days and different chat sessions?
It is an architectural sleight of hand. It is not learning your dog's name. When you mention the dog, a separate script saves that specific text string to a hidden traditional database on your account profile. The next day, when you open a brand new chat, the system silently grabs that text string and aggressively pastes it into your hidden system prompt before you even type a word.
Oh, wow.
Yeah, it forces the model to wear the tinted glasses of your dog's name every single time.
So it's forced context, not permanent learning. And what about a RAG, Retrieval augmented generation, where the AI searches the live web or digs through your company's secure documents to answer a question.
Exactly the same mechanism. The AI is not learning the company documents.
Yeah.
A standard search engine finds the relevant paragraph, pulls the text, and silently pastes it into the context window alongside your prompt. The model is reading the text in real time. It's reading, not learning. The factual knowledge lives exclusively in the retrieved document, not in model's weights.
Okay, if we accept this reality, that the model is just a frozen statistical compressor manipulating transient mathematical vectors with absolutely no permanent physical connection to the world, we have to confront the cognitive and philosophical debate raging in the sources, the symbol grounding problem.
This originates with cognitive scientist Stephen Harnad in 1990. The symbol grounding problem asks a devastating question. How can symbols in a formal enclosed system ever acquire intrinsic meaning? If an AI mathematically manipulates the token for apple, does it actually know what an apple is if it has never bitten into one, never felt the crunch, never experienced the sweetness on a tongue?
This instantly brings to mind philosopher John Searle's famous Chinese room argument. Imagine I'm locked in a room, I do not speak a word of Chinese, but I have a giant, incredibly detailed rulebook that tells me, if you see this sequence of Chinese characters, output this other sequence of Chinese characters. People outside slide questions under the door. I follow my statistical rulebook and slide perfect Chinese answers back out.
The people outside would be entirely convinced you are a fluent, conscious speaker of Chinese.
But I'm not. I don't understand a single word I am writing. I am just a meat-based processor following statistical rules. I have syntax, but zero semantics.
And in modern AI, this has evolved into what the literature calls the vector grounding problem. LLMs don't even manipulate recognizable symbols. They manipulate high-dimensional numerical vectors. Critics argue that these models are hopelessly trapped in a massive, self-referential web of statistics.
Right.
They lack what philosophers call intentionality, the capacity of a mind to be directed at or about objects in the real world. Because they have no sensor-motor experience, no physical embodiment, they cannot truly comprehend meaning. They are just the Chinese room running at 1 trillion operations per second.
But the sources also highlight fierce pushback against this pessimistic view. The proponents, categorized as internalists and externalists, have incredibly compelling counterarguments. Let's look at the internalists first.
The internalist view focuses on the origin of the data. They argue that the training data, the trillions of words on the internet, was not generated in a vacuum. It was written by human beings.
Who do have sensoromotor experiences.
Exactly. And human beings have direct causal connections to reality. Therefore, the LLM can infer the causal and informational relationships of reality directly from the linguistic traces we leave behind.
It's like a detective reconstructing a crime scene just from the footprints and the broken glass. The text itself encodes the physics and rules of the real world. And the externalists.
Externalists draw heavily on philosophers of language like Hilary Putnam and Saul Kripke. They argue that a word's meaning is anchored by its causal history. When an LLM outputs a highly accurate factual paragraph about Abraham Lincoln, that statistical token inherits its reference to the real historical person because it is connected to a massive unbroken chain of textual evidence that traces all the way back to people who actually met Lincoln. The model participates in our linguistic community, therefore its words have meaning.
So, if we pull this down from the ivory tower and connect it to the bigger picture, here's my question for you sitting there listening. If GPT-4 takes the U.S. bar exam and it beats 90% of human lawyers, which the empirical benchmarks confirm it does it actually matter philosophically if it doesn't experience the law? If the functional competence is utterly identical or even superior to a human expert, is this entire debate about semantic poverty just a pedantic academic thought experiment?
That is the defining question of artificial intelligence in 2026. And the tension between functional competence and semantic poverty remains completely, stubbornly unresolved.
Which brings us crashing down from high philosophy into the gritty realities of building software. Because if we accept that this machine is a frozen, ungrounded statistical engine, what does that mean for the developers trying to build reliable applications with it? It means you have to build systems that account for its inherent brittleness. Let's start with a concept the sources call the alignment tax.
We discussed RLHF and DPO earlier. The process is used to make a model safe, polite, and refuse dangerous requests. But that safety comes at a severe cost. The alignment tax is the phenomenon where making a model safer actually degrades its core reasoning capabilities and factual accuracy.
Why does being polite make it dumber?
Because you are mathematically forcing the model's output probabilities away from their natural pre-trained distribution. The base model learned the statistical reality of the internet. When you align it, you essentially tell it, ignore your foundational statistical instincts when someone asks a sensitive question.
That sounds problematic.
It is. That forced deviation creates mathematical ripples throughout the neural network, often crippling its ability to perform abstract logic or retrieve obscure facts. The tax you pay for safety is a loss of raw performance.
And this ties directly into the phenomenon that drives users crazy hallucinations. People constantly treat hallucinations like a bug in the code, like a glitch that just needs a software patch.
It is absolutely not a bug. It is the defining feature of the architecture. The model is fundamentally a predictive engine. It is mathematically designed to fill in the blanks with statistically plausible text. It is a chronic pleaser.
A chronic pleaser, I like that.
If you ask it a question and it does not have high-quality, high-probability factual data in its weights to answer it, it does not stop. It smoothly and confidently generates a highly plausible-sounding falsehood. It literally does not possess a mechanism to know what it doesn't know.
Okay, so knowing all this brittleness, let's step into the shoes of a local developer. Imagine you're working at a mid-sized company. You have limited hardware, maybe a single consumer-grade GPU under your desk, but you want to customize one of these open weights models for your specific business logic. The sources give us a phenomenal, deeply technical breakdown of the modern developer workflow, specifically relying on the Unsloth library.
If you are a developer without access to a massive data center, parameter-efficient fine-tuning, or PEFT, is your saving grace. Doing a full fine-tune on a modern model requires updating all 8 billion, or 70 billion weights. That requires massive server farms and astronomical costs.
Right, impossible for a small team.
Exactly. Instead, the industry relies on LoRa low-rank adaptation.
I want to understand how LoRa bypasses the memory requirement, because it sounds almost too good to be true.
It relies on matrix math. LoRaWave freezes the giant pre-trained base model entirely. You are not changing the foundational knowledge. Instead, it mathematically attaches tiny, low-rank adapter matrices to the sides of the transformer layers.
What does low rank mean in this context?
Think of a massive high-resolution photograph. That is a high-rank matrix. Contains a massive amount of dense information. But what if you compress that photo into a tiny, blocky JPEG? You lose the fine details, but you capture the broad strokes. That is a low-rank approximation. LoRa trains these tiny mathematically compressed matrices, often representing less than 1% of the model's total parameters. You only run gradient descent on those tiny adapters. It slashes the VRAM requirements by over 90% while maintaining almost all the accuracy of a full fine-tune.
And then the sources pair that with QULAR. The Q stands for quantization.
Yes. To cram a massive model onto a single 16 gigabyte or 24 gigabyte GPU, you have